Hi, Assalamualaikum. My name is Masmira. Today I am going to share to you about subtopic in mathematical modeling, which is 3.1 abstraction and scale, and 3.2 geometric scaling. Okay, we may start now. Okay, first about 3.1 abstraction and scale. My other friends in my group is Farah Izzati binti Ahmad Rizal and Muhammad Hafiz bin Muhammad Zulkifli. Okay. They will explain about the other subtopic. First, abstraction. Abstraction means process of abstracting the underlying structures, pattern or properties of a mathematical concept, removing any dependence on phenomena objects which it might originally have been connected and generalizing. The first point in abstraction is pattern from one mathematical concept can be generalized to other similar objects in the same class. The second point is technique and method from one area can be applied to prove results in other related areas. The last one is it reveals deep connections between different areas of mathematics. Okay, let me make it clear. If we see a ball, we will think about the ball, such as the shape of the ball is blah blah blah. Oh, the color is orange, for example. So I will relate the abstraction like the first impression. So in this case, uh, abstraction is first impression towards a model that we want to use it. Okay. Next, scaling. Scaling is used to reduce the number of parameters in a given model and does not necessarily yield dimensionless quantities. The first point in scaling is required the magnitude of size of quantities measured. Next, in Einstein's general theory of relativity, the mass of a particle moving at speed v is given as a dimensionless fraction of the rest mass m naught by. So this is the equation from Einstein general theory in scaling. The last point is the scaling issue is ensuring that the square of the dimensionless speed ratio is always much less than 1. Okay, next 3.2.1, which is geometric scaling. Geometric scaling is the scale factor is the ratio of two corresponding side lengths of similar figures. Similar figures have the same shape but different size. The first point is the scale factor will be less than 1 if it begins with the smaller figure, and it will be greater than 1 if it begins with the larger figure. The next point is the scale factor from the first figure to the second is always the reciprocal of the scale factor from the second figure to the first. And then I will show to you how to find a scale factor. In method 1, we should verify that the figures are similar. Second, find a corresponding side length on each figure. Third, set up a ratio. And the last one is simplify a ratio. Method 2, the first one is find the side length of the figure. Second step is determine whether the scaling are up or down. The third one is multiply one side length by the scale factor. And the last one is find the remaining side length of the figure. Okay, next we will continue and proceed to Farah. Thank you. That's all from me.
Okay, my name is Farah Izal binti Ahmad Rizal. Okay, I will present to you about subtopic 3.2.2, linearity and geometric scaling. Okay, geometric scaling arguments also can be used to demonstrate some ideas about linearity when the contexts are similar geometrically. Okay, then based on the demonstration, the relationship volume and height is nonlinear for the conical glasses by using the formula. Then, for the conical glasses, the radius vary with height, and the volume of a cone with semi-vertex angle fill to height. Okay, and as we know, radius we use as r, semi-vertex angle for alpha, height for h1 and h2, and volume for VCY. Okay, second, about subtopic 3.2.3, log plots of geometric scaling data. Well, when we use a logarithmic scale, uh, there has an advantage. Okay, first, cover a large range of value since the use of the logarithms of the value rather than to a more manageable size. Okay, second, it may contain exponential loss or power loss since this will show up as straight line. Okay, the definition for log plots of geometric scaling data is a algorithmic scale. Log scale is a way of displaying numerical data over a very wide range of value in a compact way on both the horizontal and vertical axis. The relationship of the form y equal to ax power of k appear of a straight line in a log graph. The power term corresponding to the slope and the constant terms corresponding to the intercept of the line. Typically, the largest number in the data are 100 or even 1000 of times larger than the smallest number. Okay, logarithmic axis cannot contain zero or negative number. Finally, for 3.3 subtopic, size and function for bird and flights. Okay, why the efficiency of flights varies by size? Scaling has become a major element in bird flight analysis. Okay, it has been shown to be a useful way to predict how different mechanical, physiological, and ecological parameters change with scale, morphology, and behavior. Then, scaling is also misinterpreted. The size dependence of adaptation constraint relates to allometric consistency in the morphology of avian flight, and many of these limitations can be directly related to flight mechanics. Okay, that's all from me. Thank you.
Okey, terima kasih Farah. Saya Muhammad Afif bin Muhammad Zulkifli. Saya akan menerangkan secara ringkas mengenai topik 3.3. Untuk topik 3.31 adalah the power needed to hovering. The object hover through whatever mechanism we choose. The problem is there is no working being done because the object does not affect its position. But this is definitely not accurate because in order to keep an object stationary above the ground, like a rocket engine will have to burn fuel, and a helicopter will also have to burn fuel to keep it rotor tuning. What is learned from dimension analysis is the downward force of second Newton law, which is in watt or Newton, mass per second is what is needed. So we need mass per second factor to come from somewhere, that is for sure. Power needed adalah power yang diperlukan, yang dipengaruhi oleh environment seperti jisim udara, hal laju udara, ketepatan udara dan lain-lain. Okey, untuk 3.32 adalah the power available for hovering. Okay. The power available adalah satu tenaga yang dihasilkan oleh badan kita sendiri ataupun boleh dikatakan dihasilkan oleh dalaman kita. Three ways to estimate the power. Ada 3 cara untuk kita mengira. Untuk yang pertama adalah heat loss during hovering, the rate at which is Earth supplies oxygen, and the maximum stress in its bone and muscle. Ini adalah 3 cara di mana mempengaruhi penghasilan power available. Heat loss estimate is simple. It's not altogether compelling. Muscle turn mechanical energy at 25% efficiency rate, and then when heat transfer it will decrease the rate proportional to length, like power proportional to L square. To find the available power is proportional to L square because it is proportional to the oxygen flow and it's proportional to the rate of blood delivery. Principle of conservation of energy, muscle force times contraction, limbs mass time V square. And then the power exerted by the muscle power proportional to muscle force time contraction divided by time. Okay, for 3.3.3, so there is a hovering limit. So we can see the power needed for flight is proportional to L to the power of 7 divided by 2. So this is from 3.3.1 and this from 3.3.2. The power available to the bird to sustain flight is proportional to L square. The power proportional to muscle force time contraction divided by M, like this. So we will get L square. So the power needed to hover increase so much faster than the bird size. That is a limit to hovering size must indeed exist. Boleh kita katakan limit ni adalah salah satu batasan. Kerana in real life we know everything has a limit. Kita tahu dalam kehidupan kita ni setiap sesuatu perkara mesti ada limit. Kerana itu adalah fitrah bagi setiap manusia dan benda-benda hidup. Okey, terima kasih.